Welcome to the AP review on electric fields and electric flux. Here are basically your equations that deal with electrostatics dealing with field and flux. Your equations over here on the left side are basic calculations of field, force, and your base equations for electric flux. Gauss's law and Coulombs law, your big laws that you're going to use to calculate electric field, and we'll go into those more in just a minute. Your reference equations for different charge densities, those come into play mainly when you are doing derivations. And then your electric fields for specific different charge configurations. With the format of the exam being mostly written, it's unlikely that you're going to write out a full derivation. However, they may have you talk through parts. The other thing that's important to recognize in these is conceptually thinking about what's proportional to what. Okay, so you're just kind of going down the list. Your electric field there for a ring, charge, more field. Your distances, x being that distance on the axis away from the ring, a being the radius of the ring. Okay, electric field to a charge rod, again Q, and then you have your factors of your distance and your length coming into play. Electric field due to a charged disk, you've got your factors here of distance and radius. You also have your charge density there. Then when we get down below, electric field due to a line of charge, inversely proportional to that distance from that line of charge. And then the amount of charge is also embedded in the charge density there. Okay, your electric field due to a plane of charge. Okay, and that would be an insulator or somewhere that the field goes outward in both directions, and that's why the factor of 2 is in the denominator there. And then the field outside of a charged conductor where there is no 2 in the denominator because the field inside the conductor is 0, and there is only a field outside the conductor, which makes it stronger than if that was an insulator. The important things to recognize here is they work very close to a conductor and insulator, and they're constant. They do not depend on distance. Now, you have to have either an infinite sheet, an infinite plane, or stay such that your distance away from the surface is much, much smaller than the dimensions of the surface, and you are centered more or less to be able to apply those. Electric field. Direction of electric field, always the direction of a positive test charge will experience a force. So when you're trying to draw an electric field, just draw a little positive test charge and then compare it. What happens to it there? For example, in the diagram I drew near, it would experience a force of attraction to the negative and a force of repulsion away from the positive, and then your field would be the vector combination of those two. So overall, the idea of electric field is how many newtons of force are acting on a coulomb of charge at that location. You know you have an electric field if you have a charge in a region in space where it will experience any electrostatic forces. So you have different field configurations there. Remember, field lines are always initiated perpendicular to a charged surface or terminate perpendicular to the charged surface. Field lines never cross each other because that would indicate that a charge is being told to do two separate things at the same location, which cannot occur. Okay. Also, we talked about equipotential lines. If I draw on an equipotential line down here on the bottom, those equipotential lines are perpendicular to the field lines, and they indicate a direction you could move the charge without changing the electric potential without changing without doing any work on the charge. So you're not moving with the field. That would mean that the field is doing work. You're not moving against the field. That would mean that you're doing work. You're moving to the side or perpendicular to the field lines. Electric flux, E dot A, or the integral of E dot dA. Remember, that's electric field times the area times the cosine of the angle between E and A. That area vector, that's just a vector that's perpendicular to the surface. It has a length that's numerically equal to the area of the surface. So on the figure I have above, my area vector, let me choose a color that will show up. My area vector right there, perpendicular to that surface. Okay, my area vector on the other one, right there, again, perpendicular to the surface. So then you can adjust the amount of flux based on really the direction of that area or that area vector. Remember, the area vector is perpendicular to the area. It's not the plane of the area, so watch for that wording. So overall, conceptually, electric flux is really dealing with how much field intercepts an area. And electric flux is a tool that we mainly use in Gauss's law. Your values, more area, more flux, okay, more field, more flux, and then you can adjust the value based on that angle also. So then when you're deriving electric fields or analyzing the derivations, your two basic tools are Coulombs' law and Gauss's law. Coulombs' law always works, no matter what the charge configuration is. If you're patient enough to do the calculus, Coulombs' law will always allow you to calculate what that electric field value is. Gauss's law only applies to symmetrical situations, and you should recognize these equations by name because the AP will sometimes discuss them by name. Gaussian surface, that's just an imagined closed surface, and it typically encloses a charge. So then down here, I have two different Gaussian surfaces here. So for my field over here to the side, I could take my Gaussian surface there, and it encloses that charge. Now, note that it is a three-dimensional surface. So it's not just a circle there, that would be a sphere. I could place my rectangular prism around that charge, and the amount of flux that either one of those encloses when it's around the charge is exactly the same. I could take my surface and move it here, move it there. I could move it various different places, and as long as it encloses all the charge, then the number of field lines penetrating that surface is going to be the same, and the flux is the same. So the Gaussian surface you choose is arbitrary, but you want to choose it such that it's easy, such as the sphere, so that the area vector would be parallel or perpendicular to the field, so that the field is constant or zero at all points, and you need it to be a geometric shape, not a random shape, so that you can use a geometric formula to be able to calculate. Okay, now let's talk about placement of this Gaussian surface. Right now, where I have the sphere around the positively charged object, we can use that to be able to calculate what the electric field is, because we enclose charge, and the enclosed part is very important. Okay, I've enclosed charge, I have a flux there, I can calculate a field. Now, if I move that sphere over here, I do not enclose any charge. Now, if you think about the region inside that sphere, there is an electric field. okay, because you're around a positive charge. But by Gauss's law, you get zero. That's not zero electric field, that's zero flux. Okay, so when you are using Gauss's law, if the number of field lines that enter one side match the number of field lines that exit the other side, or in general, the number of field lines that enter is the same as the number of field lines that exit, then your flux is going to be zero. That does not necessarily imply that the field is equal to zero at any of those locations. Okay? Now, other important things here to remember. Just some references, your force equals kq1 q2 over r squared and E equals kq over r squared. These apply only to point charges. Your two surface equations. Surface charge density over epsilon naught and surface charge density over 2 epsilon naught. Those are handy references near the surface of a conductor, near the surface of an insulator. Remember that conductors, charge spreads out on the surface. If it's an insulator, then the charge stays exactly where you place it. But if it's a conductor, the charge will spread out on the surface. If it's a uniformly shaped conductor like a sphere, it will spread out evenly. If it's not uniformly shaped, if you have like pointed or jagged edges, then the charge tends to gather more towards those jagged edges. Inside of a conductor, the field is zero because all the charge resides on the outside. If there was any net charge on the inside, it would reconfigure until there was zero field. That idea is known as electric shielding. If you're inside an insulator, you can still have a field because you can have net charge inside of an insulator. Other useful equations that relate to field. V is equal to negative ED, or ED equation. The negative is mainly a directional thing in terms of who's doing work, you or the field. And ED only applies when the field is constant. If your field is not constant, you can use the integral. V equals negative integral of E dot ds. And then you have your force equation, F equals QE. I'm going to throw in one other variation of ED. If we take the calculus version and we solve down for E, that's going to give us negative dV dx. Or if we were in the y direction, negative dV dy. Remember, when you take a derivative, that is a slope. So that's useful in terms of if you're analyzing a graph of potential versus distance. The slope is the field, okay? And this can also be useful if you're deriving electric field and you know an equation for the electric potential. You can merely take the derivative of that electric potential equation in your different respective directions to be able to get the components of the electric field. Ponder physics.